Do we have all of you? Cho tên này
So we would so it's a bit more relaxed for my appearance. And thank you, and enjoy your time. Thank you for studying.
Wait for a minute because my name is going up and close the door. Okay, the sun is like rushing here.
Yeah, that's a bit too bright.
See that so you have a 60-centimeter telescope here. It was once upon a time the biggest, but it was in 1869, and it's still in use. Still in use. Okay, now the light's gone. Okay. I think we're ready to start. Thanks for joining. It's a pleasure to welcome Dr. Terese Hansen today from Stockholm University. She, as you all know, she's here for the NEO School as a tutor, but not speaking today. So we managed to grab her and get her out of the NEO School for an hour. So thanks so much for agreeing to that. Terese did a double PhD from the University of Heidelberg in 2015. After that, she was at the Carnegie Institute for Science for 3 years, and then I forgot. So then I went to Texas, right? Then Stockholm. Great. So she'll tell us about hunting for gold or more realistically uranium.
Well, thank you very much. Thank you for the introduction. So since there's not a lot here, just please interrupt me if you have questions and stop me, and we can talk about things. We don't have to get through all of my 40 slides today, but we'll see. Yeah, so I'm gonna talk to you about something that I've been working on for the last 10-ish years now. It's part of the Art Process Alliance, which I'll get into what that is. But usually I show, here we go. This, oh, can we get rid of the, sorry, I should have tried to get rid of that. How do we do that? Is there like a more thing? How do you do? Hide video panel?
Over it and just pull it.
Well, I don't know if I can pull it because I.
Can you hide the?
No.
Okay, just over the mouse to just pull it down.
So that will.
Yeah. Yeah. If you just you can pull it away. That's right.
Okay. Right.
Maybe all the way down.
Yeah, maybe we can put it down here. There's not much going on down here. Don't seem to be able to put it on the screen. Okay, sorry about that. So I usually put up this version of the code table to sort of explain what it is I do. I'm a cell spectroscopist, and my main interest is to figure out how this whole periodic table came about, so how all the elements were formed, and I do that by looking at their absorption features in spectra of stars. And at the moment, as you might have noticed from the title of my talk, I'm particularly interested in the very heavy elements. So we have gold here, and we have uranium somewhere down here. And so all of these elements are basically everything beyond iron is produced by neutron-capture. So we have 2 neutron-capture processes. We have the slow process where you have your C nuclei that gets bombarded with neutrons, but at a pace where once you create something unstable, then it's time to beta decay, and then you build up elements that way. But then we also have the rapid neutron capture process, which is what I'm interested in, or the ARC process, where the bombardment of neutrons is so fast that the isotopes that you create do not have time to decay, and you get this process that basically moves extremely far away from stability, and then when the neutron flux shuts up, it decays back to stability, and you get all of these lovely elements like gold and uranium. Basically, our process is responsible for creating half of the isotopes heavier than iron in the periodic table, and the S process, the slow neutron-capture process, creates the other half. The problem with the R process is that we don't really know where it happens astrophysically. So there was, of course, this lovely neutron-star merger, which you probably all remember in 2017, where we saw two neutron stars merge. We saw the gravitational wave. We followed it up with basically every telescope on Earth was pointed to this event, and we got these beautiful light curves where we saw evidence of the decay of lanthanide material, so these heavy elements. But it's very difficult to figure out what exactly was made in that event. I think we have measurements of strontium and yttrium, but certainly not gold. We don't actually even know if that event made gold. We don't know how often these events happen. We don't know if they happen early enough to be sort of the main source of our process elements in the universe. So there are other theoretical options like collapsed stars, which are these rotating massive stars that basically, instead of exploding as supernova, they collapse. But in that collapse, they have this disk of material where you can have an R process. There's also the regular core collapse supernovae, which may contribute to light elements like strontium, yttrium, zirconium. And then there are these jet supernovae, which are also really fast rotating massive stars, which then have some extreme magnetic fields that creates these jet outflows, where in those jets you can have an R process. But the question is, which of these contribute? Do they all contribute? Do they contribute at different times? What is the sort of production and evolution of these elements in the universe? And the way I do this is basically what's called nuclear astrophysics with abundances. So the general idea is that you have this nuclear synthesis event, neutron merger or something. It puts stuff into the interstellar medium. Then you create a low mass star. That star lives on today. And in the atmospheres of this star, you have these elements that were created in this event. So I go to my favorite telescope. This is the 2.7 meter McDonald telescope in Texas. I get a spectrum, and then I look for something like this, which is the europium line. And then I get an idea about how much europium is in that star, and that more or less directly translates back to the europium produced in this event. Obviously, this requires a special type of stars. We can't just go and look at the sun, because the sun is really young. And the sun is the chemical composition of the sun is the cumulative of, well, 14 point something giga-years of chemical evolution. So we need the metal 4 stars. We need to go back in time. So we need to basically get not this first generation, because they were probably massive and exploded, but we need to get this second generation of stars. And very luckily, when we do that, our spectrum also gets much more simple to look at. So down here you have the spectrum of the sun, which is a mess. There's so many lines that continue, is really hard to find. But then when you go to lower metallicity, you get a more chemically extreme stellar atmosphere. You also get a much nicer spectrum to work with. There's not that many of those stars, but we find them and we look at them. And when it comes to the R process, we are actually quite fortunate, because a number of these stars, not a lot, about 5% of these MEL4 stars are enhanced in the R process elements, which means that the lines of these elements show up in the spectra. So up here you have a spectrum of a normal MEL4 star, which is red, and an R process enhanced MEL4 star, which is the blue. And you see we have all these lovely features like europium, dysprosium, cesium, lanthanum, and also elements that I can't pronounce. But that means that we can actually we can actually derive abundances for these elements in these very MEL4 stars, which we otherwise wouldn't really have a chance of. And what you see down here at the bottom is just the different elements that we can actually get if we're lucky enough to find a star that is highly enhanced in our process. So all the elements here in blue are things we can get from optical spectrum from the ground. And all the red ones are ones that we can get if we get time on the HST and go to space in the spectrum. So we can get a very complete abundance pattern of these stars to investigate these R process events. And people have done that for some years now. So this is a plot of the first R-process enhanced star that was ever found. Some of you might know it as the Sneeden star, because it was Christopher Sneeden who discovered it. And you're going to see a lot of these plots throughout my talk. So what you have here, this is sort of standard what we do with stellar abundances and the R-process. So we plot the absolute abundances as a function of atomic number. And then we scale our pattern, or scale the solar system pattern to our abundance pattern in the star. That's because that was what they did with this very first star. So if you see over here, you have the solid line, the points are obviously the stellar abundances, and the solid line is the solar R-process abundance pattern. So basically, the abundance patterns of the R-process elements in the sun, this very young star, scaled to the level of europium in this star. And you see this beautiful match between a star that has a velocity of -3, so it's like really a second generation star. It was born billions of years ago, and the sun that was born yesterday, which is quite impressive. Doesn't go quite so well for the light elements, and we'll come back to that later. They go back and took more or better spectrum of the star, and then they filled out this entire range. And basically, they say that this pattern is really good when you go from sort of barium and up to hafnium. So this lanthanide region, you have a really, really good match between the R-process elements in the sun and the R-process elements in this very old star. So that led them to conclude that it has to be a very robust process that makes these elements, because it has to sort of spit out the same ratios, not the same amounts, but the same ratios each time it goes around. And as time went on, people found more stars, and they continued to see this very consistent pattern. So these are, 6 R-process enhanced stars in the solar pattern. Well, I think actually the pattern is the CS22 star that I showed you just before. But again, you see in this middle region, this lanthanide region, we have very little scatter between the scaled pattern and the abundances in the star. Light elements, okay, there's something going on there. Actinides, thorium, uranium, yes, there's also something going on there. And this was sort of the state of the field up until 10, 15 years ago. And that's, I mean, the first R-process enhanced star was discovered in the 90s. And then even sort of 20 years after, this is kind of what we learned. We had a very robust main R-process. We had some scatter out here. There's lots of suggestions as to what that was. There's some scatter out here, lots of suggestions as to what that was, but not really any major progress. And that's because, well, yeah. So why not? Since I told you that we could get all these lovely elements from the spectra of the stars. I mean, if you look at these patterns, there's a lot of stuff that, I mean, this guy, for instance, doesn't have anything over here. There's some gaps over here as well. And this light part of the pattern is not really well populated. So why don't we just go and get all these abundances for all the stars and figure out what is going on with this R-process? Well, it's kind of hard. We have lines that are easy to investigate in the stars. We have like strontium, barium, europium. Sure, we can get those in all of our stars, no problem. Then it gets a little bit more difficult. Then we stuff like silver, or palladium, silver, osmium. So this light element part that we don't really know what's going on. And also up in the third peak, the lines get really weak, they get blended. Even though these are highly R-process enhanced stars, it gets kind of hard. And then there are the ones that are just almost impossible. Stuff like uranium. Up until last year, we basically only had this one uranium line to look at in the wing of this massively strong iron line. So it was really hard to get these abundances. And that resulted in basically this sample of R-process enhanced stars before 2016. So as you see, they're all pretty faint, which means that it's really hard to get high-resolution high-signal spectra, which also means that the number of neutron-capture elements abundances derived per spectrum is kind of low. Most of them only have like about 10 maximum. And the ones where we really have the full pattern, well, that's only a couple of stars. So what do we need? Well, We need more stars. We always need more stars. We're still exhausted. I always need more stars. But I also need brighter stars because it really, I mean, it's going to take too much telescope time to get these, to get the abundances I need in the stars that we know. And another thing, which I haven't touched about much, and I don't really want to go into, but you can ask me, is all of these stars that I showed you before were analyzed in a single analysis way. So people found a star, analyzed it, another group found a star and analyzed it, a third group found a star, analyzed it, and you know, astronomical analysis, while it should be homogeneous and comparable, it is not always the case. And that is definitely not the case with stellar abundances. So we need to homogenize the analysis to make sure that the differences that we see is actually differences and not just offsets in temperature scale or something else. And this is where the R-Process Alliance comes in. So we are a group of stellar spectroscopists that got together in about 2016, I think. There's a little discussion about that, and said, "Hey, let's do something about this problem." So what did we do? Well, this is sort of our grand big plan. We're not quite there yet, but we will be there, because we want to basically combine all the observations, so not just stellar spectra, which is you see down here, but also kilonova observations. We want to combine that with the nuclear properties of the reactions that happen in the R process, and then we want to constrain the conditions of the R process site. But at the moment, what we can do, and since we're all stellar spectroscopists, we focus on this part down here. So we focused on building a large sample of stars where we could derive abundances of R process elements and hopefully find more of these highly R process intense stars so that we would have more than 60 stars to work with. And so what we did is that we started this survey where we select bright stars, so we can observe a lot of them in a short time. We also select them to be cold, so we are actually sure that we can get a European abundance. It doesn't really matter if we can't get a European abundance, that we could observe as many stars as we like. And of course, metal poor, so that we know that when we actually get the abundances of these stars, they can be used to probe the nucleosynthesis in the early universe, as they were enhanced by one, maybe a couple of nucleosynthesis events. And then we set out to get time on all the basically 2-meter class telescope we could get our hands on. This one is the 2.5 meter DuPont telescope at Las Campanas, and this is the McDonald again, where I spent, I don't know, half a year of nights on these telescopes, gathering spectra of these stars. So we gather fairly high resolution because we need that to see the Europa line, and actually also fairly high signal to noise, at least in sort of relatively. And then we just took the snapshot spectra of the stars and we looked for this line and actually also this dysprosium line. And you see a spectrum of a non-R process enhanced star up here, and then a spectrum of an R process enhanced star down here with this massive European line, which is actually comparable straight to this iron line next to it. We've done this for many years now, and we've gathered stars of about 2,000, or a spectrum of about 2,000 stars. This is a lot of observing hours. You can sort of equivalent each of those to one observing hour, about 2,000 observing hours probably. And then we derive abundances and we classify them. And we basically classify them into these 3 categories. We have the R2 stars, which are these highly R process enhanced stars, so massive European line, more European and then barium, because that's the signature of the R process. We have a lot of these R1 stars, which are just mildly enhanced in European. And then we also search for these limited R stars, which don't really have a lot of European, but have a lot of strontium. So this light element in the fuzzy region I was talking about. I'll come back to that. Oh, and this is just, might be a good place to put in that there are abundances they're not measured, and I might say measured. I'll try very hard not to say measured. But they're definitely model dependent. So this is sort of an overview of what we do. We have some atomic data. We have a model atmosphere, which is, in our case, all 1D and local thermodynamic equilibrium. And then we have our spectrum, and then we put it through a radiative transfer code. And then we get a synthetic spectrum. So what you see over here is the synthetic spectrum is the green line, and the observed spectrum is the points. And we have a thorium line here, and we get synthesis without thorium, the spectrum is the spectrum like this. So we get a thorium abundance out for this star. And then we have this bracket notation where we put the thorough abundances on a scale reference to the sun. We also have this absolute notation, which is what we use most when we talk about the R process. But yeah, definitely mod dependent. There we go. Okay, so as I said, we've been doing this for some time now, and we published 4 data releases, and where we have published the abundances for 600 stars. As I said, we've actually collected spectra of 2000, so we're in the process of analyzing that massive sample. But just in the 600 stars that we have looked at, we found 32 new R2 stars. So this is the ones that there were 60 of before we started. So we doubled the sample. We found a whole bunch of these R1 stars and also quite a bunch of these limited R stars. And what you see here is just the europium over iron as a functionality for all 4 data release papers. And you can see all the R2 stars are marked up here with red squares. The faded ones are just from previous data release. This is from the latest one. All the R1 stars down here, the non-R process enhanced stars, the gray dots, and then these limited R stars down here. And actually this prompted, so the division line between an R1 and R2 star before we started this survey was actually set at 1. But this larger sample actually prompted it to be put down to 0.7 because that makes it more sense. Still kind of arbitrary, and we'll look into that, but there seems to be something going on at the 0.7 line. Okay, so this is all our lovely data. Of course, I should say that when we then find these highly R-process enhanced stars, so all of these R2 stars we find here, where we will know that there are lots of lovely absorption features in the spectrum, we go and we take what we call portrait spectra. So these are these extremely high resolution, so R of 80,000 or more. Extremely high signal noise also. We want signal noise of 100 at this around 3860, which is where the uranium line is that I showed you. To be able to do a complete analysis of the highly R-process stars. So we have got about 90 of these portrait spectra collected so far. We've also published quite a few papers. I think we're on, what, 15 something portrait papers that we published so far. And one of the things that we found is the golden standard. And here's the gold for my title. So this is a star that we got a optical spectrum and saw that it was highly R-process enhanced. Then we got UV spectra, so we got HST, and we basically got all the wavelength coverage in the world. And we then were able to grab abundances for 63 elements total, 42 neutron-capture elements. Those are ones that I showed you. This is the object outside the solar system which has the most complete chemical inventory so far, which is quite impressive, we think. Yeah, we derived the abundances. We did the standard scaling, so you have the absolute abundances of the x-axis and atomic number on the y-axis, sorry, x-axis, y-axis. And if you scale to the solar system for europium, that's somewhere here, you again see this beautiful match, actually extended all the way up to lead, maybe. Something's going on down here in the light element end, and unfortunately we didn't get uranium in the star, but the thorium seems to match quite nicely. But yeah, we would like to advocate for this as the R-process template. So a lot of people, when they do R-process modeling, they use the sun, which is really a bad idea because there's all this stuff going on in the light element end. So please, if you do neutron star merger nucleosynthesis modeling, this is your stellar template that you need to match your abundances to or your yields to. Speaking of gold, so we did get gold in this star because we got HST spectra. And just because there's gold in my title of my talk, I just wanted to show these other two stars, Well, we also have HST spectra. I think we have a few more in the pipeline where we also got these gold lines, but gold is pretty hard because, as I've mentioned a couple of times, you have to go, it's far in UV, so you have to get HST spectra of it. So we're not going to increase the gold sample by that much, but I think we actually have doubled it so far. Anyway, let's get to some of the other interesting things that we've done with this RPA sample. So I showed you this plot in the beginning, said, okay, this is what people have found out, that we have this scatter in the light end, we have this very homogeneous, robust pattern here, and then the scatter over here. But it turns out that if you split the pattern into two, and then you scale the light end to zirconium, and you scale the heavy end to europium, where's europium? There, still. You actually get some sort of universality in the light end as well for strontium, yttrium, zirconium, sort of up to ruthenium-ish. So it seems to, all these, well, so it seems that there's not just a robust main R process, but there's also a robust light R process. And the reason why we have this scatter is because everything was scaled to europium here. So basically what you just have is different ratios of the two components of the pattern. And that we can use because that is basically what we call the Landmark fraction. So we can use that to say something about the kilonova because the Landmark fraction was also measured in the 2017 kilonova. So what we did here is that we took all the R process of stars that we know of in basically all the stars in the literature, which had a barrier to europium less than -0.4. So we knew it was an R process, and then we calculated this Landmark fraction, and then we compared it to the 2017 kilonova. So the blue line here is basically all Mel-4 stars with this ratio, and the orange line is the highly R process intense stars. And actually, what you can see here is that the Landmark fraction that was in the kilonova is too low. Well, the kilonova basically did not produce enough Landmarks to match what we observed in the stars, not even for just the regular Mel-4 ones. I mean, sure, maybe you can say that this box here is agreeable with the blue curve, but it's definitely not agreeable with the orange curve. So if kilonova or if neutron mergers are the main source of our process elements in the world, we need some kilonova that produces a lot more heavy elements than was produced in 2017. We don't know if that was an oddball, that may have been an oddball, but we definitely need some that do more. And we can use this. So I'm not a neutron merger expert, but I believe that this basically this ratio between the light and the heavy can be probed as a ratio between ejecta. So the really Landmark rich ejecta comes from the tidal ejecta, and the more light R process ejecta comes from the wind. So you can sort of use this Landmark fraction in the star to say, okay, well, how do my kilonova need to, how do my neutron merger need to look if I were to produce this ratio? Okay, so that's one diagnostic we can get out of this. But what about these? There's still some scatter going on here, right? This universality that we see here and over here really does not extend to this region. Well, we have a theory about what is going on there as well. And the theory is that that region is heavily influenced by fission fragment deposition. So when you have an R process, it goes to extremely heavy nuclei, and at some point they fission. And the products of that fission, we think, or the models say, land back in this area. So basically changing the abundances of these elements. So what you see in this figure is again this pattern that you've seen before. So you have the absolute abundances over here, the atomic number, and then the green line is a baseline pattern with very low europium stars, so stars that doesn't have a lot of europium in their atmospheres, hence not a very strong R process. And then the orange lines are different models as to when you get more and more fission in this R process model. And the dots here are the data points. So, and they grow. So you have larger and larger circles as you get more and more europium in the stars. So basically a stronger arc process. And you can see that the pattern sort of increases upwards when you get to these higher and higher europium stars and get more and more efficient fragment deposition. It turns out that it may also affect this pattern over here, the heavy elements. So this universality that we've seen could actually just be because we've looked at all these extremely arc process enhanced stars that all have basically the same level of efficient fragment deposition. So if we look at a range of europium values in stars, then it will be easier to probe what is actually going on. This is work in progress. This was, well, it was published but we're trying to investigate this in more detail. Yes. Okay. So now we found out some new stuff about this main part. We found out some new stuff about this light part. Then there was this scatter over here, and this is where the uranium comes in. And the scatter over there is because we have what we call actinide boost and actinide deficient stars. So we have stars that have a lot more thorium and uranium compared to europium than the sun, and we have stars that have a lot less. So basically, like this one down here. The funny extra part is that if you calculate the ages, because these stars or these elements are radioactive, so they decay with very long half-life, so we can use them to calculate the ages of the stars. But if you do that for an actinide boost star, you basically get a negative age. So the star was formed before the universe. If you do that with an actinide deficient star, you get an age that's longer than the universe. So yeah, there's clearly something going on there. But again, this is also depends on production ratios in the models that we have, which are not really there yet, because I mean, the abundances are there. This is what we see in the stars. But we are doing something to look into that as well. We still don't really have that many abundances, but the arc process alliance has actually detected uranium in 4 stars so far. 2 of them are still to be published. And that is doubling the literature sample, so going from 4 to 8 stars. And this is just by looking at the 600 stars that we looked at so far. There's another 1,400 stars to look at. And one of the things that we've worked on to increase this sample is which lines to use. So basically, as I showed earlier, people have been using this very, very weak uranium line at 3859 angstroms. It's very far in the blue. It's heavily blended with other things. It's in the wing of this iron line. It's really, really hard to model. However, we had a graduate student at the University of Florida who looked into these other 2, so this uranium line at 4050 and this other one at 4090, and figured out the blends in these, figured out the atomic data for these lines. And so the last part we've detected has actually been just by looking at these 2 lines, because this line up here in this star that I'm looking at down here is completely unmodelable. So hopefully, with the advent of these new lines, we can actually find more uranium detections. Okay, so in my last, 10 minutes, 5 minutes, I will talk about, I'll go away from the Milky Way halo and talk a little bit more about what we see in the satellites, because basically, well, all I've been talking about so far, all the stars that we're looking at right now are in the Milky Way halo. But there are, of course, arc process and stars at other places, and maybe they were not born in the Milky Way halo, because as we have these, this is just sort of schematic overview. So you have these phase-coherent satellite systems where you can look at this. Then sometimes they get a little bit close, then you get a stream, the system starts to be accreted into the Milky Way halo. And then you, at some point, everything is completely phase mixed, and we have these stars in there. We can still trace them back to where they came from, though. And it actually turns out that a lot of the R2 stars that we know of were accreted into the Milky Way halo, so they were probably born in smaller systems like this. So why don't we look at some of those systems? Well, a really great place to look is these ultra-faint dwarf galaxies. You probably know of this Reticulum 2 guy that was discovered in, I think, also 2016, just before the neutron merger happened. So these are these extremely small, dark matter dominated, very chemically unevolved systems. And when we look at them, we usually see abundances that are typical for the Mercury halo stars, so similar to that. But in this particular system, they found these 7 stars. So they looked at 9 stars. All the red circles here are the Recidium-2 stars, and they found these 7 of them to be highly enhanced in our process elements. So they have this, you see the strontium, protein-velocity, barium, and europium, and they have these extreme neutron-capture element abundances. All the other color points here are all other ultra-faint dwarf galaxies that are usually very low in these abundances. Usually you can only get a limit on europium. But the fact when we find them in these systems, we can actually get an environmental constraint on the out process itself, because we know it had to happen in that system. When we look at the stars in the halo, we have no idea where they're born. We have no idea whether they were born. Well, we will soon know due to Gaia, but in principle, we don't know if they were born in the Milky Way-like galaxy or an ultra-faint-like dwarf galaxy. But here we have a small closed environment where these things have to have happened. And actually, by looking at some more stars in this system and looking at the star formation history of this system, I don't have a slide on that, I should have that. They found out that the R process event had to have happened quite early in the system, which may make it clash a little bit with the neutron-star merger scenario, because there's delay time for those. But whatever happened, it had to have had a really prolific event, and also it has to be a fairly rare event, because we don't see it in all the other ones. I mean, we see it in just one galaxy, this highly enhanced stuff. And now actually contradicting my own slide, because we do see our process enhanced stars in other ultra-faint dwarf galaxies, but not in the same way as we do in Reticulum-2. So we have GRU-2 and Tucana-3 and Tucana-5 that also have these R process enhanced stars, but these are these mildly ones. So what you see here is the strontium to europium abundances as a function of europium in all of these dwarfs. So we have Reticulum-2 over here. This is Tucana-3, where all the stars have this mild R process enhancement. And then we have Tucana-5 and GRU-2 here. And the reason why I plotted the strontium to europium ratio is that if you remember back to my abundance pattern, you had strontium on the light side, europium on the heavy side. So this ratio between the light and the heavy side can in proxy be looked at via the strontium and europium ratios, since we don't have the full pattern. So by looking at this, we could maybe imagine that the R process that happened in GRU-2 and Tucana-5 were similar to the one that happened in Reticulum-2, because we had the same ratio between this light and heavy elements, whereas whatever happened in Tucana-3 was probably something different. And there's actually also some suggestion that might be some S process contribution up here. But really, we need more stars. And a way of getting more stars is to look for systems, so the ultra-faint dwarfs are very far away, so getting more stars, those require a lot of telescope time that we don't really have. But sometimes they come in and they make these streams, and if we can find them, then we suddenly have stars that are much closer and much easier to study. And that's what we did with this in this stream that we found in the S5 collaboration. So basically all the stars in the stream showed an R process enhancement, and one of them was this Indus 13 that showed an extreme R process enhancement. And this is the abundance pattern that we were able to get for this star. So you again have the abundances on the y-axis and the atomic number on the x-axis. And as you can see, we could actually get some of these light elements that are interesting in the molybdenum and ruthenium. We could get third peak elements. We could even get thorium in this star, which is really, really hard to do in the ultra-faint dwarf galaxy spectra. And we can also say something about what type of object this was. So by looking at the melicity of the object, which is up here, we can put it onto since we know it's a dwarf galaxy because it had a spread in the melicity, we can put it onto this mass melicity plot and see that, well, it was probably not an ultra-faint, it was probably more like a classical dwarf galaxy, so something in the sense of an Ursa Minor system, which is, in the sense of chemical evolution, still a bit too messy for us to use much. But we're looking to see if we can find these streams from ultra-faint dwarf galaxies. And with that, I will give you a summary. Say, we've known the R process to happen for many years. We found the stars about 30 years ago, but in the first sort of 20 years, this progress has been kind of slow. But then the R process alliance came about, and we will deliver probably sometime next year a statistical sample of 2,000 stars, abundances for these 2,000 stars, to address some of the open questions. Some of the things that we've already found is that there's actually universality among both light and heavy R process elements, leading to these lanthanide fractions, which can be a promising way to compare to kilonova observations, which there are, by the way, only more of as we speak. And we see this variation in the light elements from ruthenium to palladium, which suggests this infraction deposition. Just to go back to the title of my talk, we have actually doubled the sample of the gold and uranium abundances known in these stars. It's a slow process, but we are getting there. And yeah, the next step is to do a full chemodynamical analysis of these stars to actually also trace the birth environment and use that as a completer of the R process. And that was it.
Thank you very much. That was a nice tour of these stars and SNR process. Any questions?
Yes. I missed. What is the process? Why do only 5% of the stars in our galaxy appear to be R processed?
Well,
so what is the progenitor? What is required to generate this process to keep going this process with stars?
Well, so as you go to higher and higher metallicity, more of them have R process elements. But at the very low metallicity, the R process seems to be quite rare and stochastic. So it seems to sort of happen in one place, and then it highly enrich those stars, but not stars over here. So
without necessarily, so we don't know
why.
Well, no. So I mean, here the neutron star mergers fits very well into that theory, right? Because those are rare events. The scatter in the European ones in the early universe has sort of is one of the reasons why we say, okay, regular core collapse supernovae clearly cannot do this, because otherwise it would be like magnesium, which is basically the same everywhere. But yeah, but it's a rare prolific event, but we don't really know what. Yeah.
And if I may, one more question. So you had like in one of those dwarf galaxy streamers, like 7% actually the stars. So
yes.
So
this one
is this 5%, 7%
well
directly comparable, or is this?
Yes, it is, because a lot of those 5% that we have in the Milky Way halo probably came from systems like this that were accreted into the Milky Way. So when you have a much smaller system, then having a neutron star merger that goes off will pollute most of the gas, right? So basically, the two stars that don't have R process was probably born before the neutron star merger went off. Then the neutron star merger went off. It's a small system. Everything got polluted. And then if we later on throw one of these into the Milky Way, well, then you have stars from all the systems as well. But then you have these small number of R process enhanced stars that will then add up to the maybe 5-10% we have in the Milky Way halo. Yes.
So whatever processes, stochastic process producing this thing, for those dwarf galaxies, it's much more efficient.
No, it's just a small environment that makes it more efficient, right? Because it's the same amount of europium that it puts out, but it's just these galaxies have something like 10 to the 6 solar masses of gas to mix the europium up into, whereas stuff like the Milky Way has much more gas, right? So if you have a neutron star merger that goes up in the Milky Way, you will not see the signature in the stars. So it's the dilution of the stuff produced. Yes.
Yes. Yeah. Thank you. Very, very interesting. Okay, I have multiple questions, but yeah, because I'm not so familiar to the spectra and in these very heavy elements. So in order to characterize as an art process, not diagnostic, I think
yeah, so I didn't get into this that much, but well, have a look at this one. So basically, so you have the R process or the S process that can make these elements. In principle, also an I process, but let's ignore that for now. And they make different ratios of the elements. So basically, in an R process, you will always have more europium than you have barium. That's just the nuclear synthesis of the process. It's just how it goes. So when we look for these stars, we look for stars that have more europium than barium. And then we usually also match them to this pattern. So the dashed line here is the solar S process pattern. So basically what people do is to take the abundances in the sun, then they calculate what the S process contribution is, because the S process is nice. It doesn't happen away from stability. You have all, all the cross section, basically everything how it goes, and you can make some chemical evolution model and say, this is what the fraction, this is how much the S process should have made of the elements in the sun. Then the rest of that is what we think is the R process. So this has lots of issues, but it creates these two very different patterns in this plot, where you have the solid line, which is the R process, and the dashed line, which is the S process. And so when we plot the abundances that we have for these stars, and they basically more or less match the R process, then that tells us it's an R process.
And this measurement here, and this probability to have a solar R process or S process, are measured by the line absorptions, ionized or down ionized, or
yes. So all of these elements are ionized. Most of them in this range are ionized species. These ones are neutral. I think a lot of these over here are neutral as well, but it's absorption features in the stellar spectrum. From yes. So basically, we go back. Here. So this is a spectrum of one of our stars, and all of this is not noise. This is absorption features. So you see all of the absorption features that we have of the different elements that we then measure.
And one more question, in the plots with the atomic number and the lines, the curves which have been plotted, they are models from a radiographic model which corresponds to a temperature in the stars or something, then the plot in the... No,
this one?
They are modeling the observations.
Sorry?
Yeah, they're...
so these are the abundances.
No, yeah. And
but they obviously
the lines, because some lines they're not so modeled in the just from comparison, or they're modeled, all of them they're modeled to the observations.
So all of our abundances are derived with spectral synthesis, which means we create a synthetic spectra, which we then match to our observations. Which is where the model dependency comes in, because obviously that spectrum will change if we change the temperature, we change the gravity, and so how we decide to do our temperature, gravity, velocities of the stars, what atomic data we put in, sometimes that's not completely known either. What radiative transfer code we use, there are different ones out there, whether we treat things in LT or non-LT, whether we do 1D, 3D models. All of that will change how, well, it won't change how the line looks because that's dictated by the spectrum, right? But it will change how much thorium is needed to create this line.
Okay. Thank you.
What is systematic? This kind of uncertainties. What's the amplitude? This is systematic.
We don't really have a very good handle on this. It also varies from element to element and from line to line, especially with the 3D and non-LT. The different If we keep everything in LTE and 1D, then I would say different temperature scales would probably change things to about 0.2 dex, which is quite significant when you compare to Japan when you look for scattering things. But yeah, something on that scale. So this is why well, one of the goals of the RPA is to say, okay, we need a very large sample where we've done everything, maybe not correct because we don't have the machinery to do that, but at least consistently. So we can say, yes, this star has more europium than that star, or more thorium, or whatever.
Yeah. And then, I'm sorry again. We see absorption lines from some elements that they are produced by nucleosynthesis in the past generation, or with our process, we only see the current produced heavy elements with our process in the stars.
Well, so the stars I look at don't produce these elements.
Yeah,
right? Yeah.
Yeah.
All of it is produced in neutron-star merger, something that happened before the star was born, and hopefully that's why I go back in the.
So we can trace how they produced in the first place, right?
Hopefully, yes.
Yeah, wow.
That's the whole point of this. That we hope to get a pattern out that can say, or basically we hope to get. Okay, going the wrong way. Sorry. We hope to get something like this out for. Right now we have a fraction of this for 60 stars, and we hope to get not entirely this because we can't do all this, but most of this for 100, 200 stars.
But to make the diagnostic, we say about the environment and the abundance of uranium and barrels. So we're not talking about the environment in the progenitor.
No. When I talk about environment, I mean the environment where the stars were born.
Okay.
Yeah.
Okay.
But that will also inform you of what kind of environment was in the progenitor, right? Because can this, in the terms of the ultimate dwarf-like galaxy, I mean, can it even contain the gas after a neutron-star merger has exploded? Is that even an option? Yeah. What do you have a star formation history? That means that you could have other sources like the exotic supernovae. Could they have happened in that environment? All that kind of thing. But the details of the abundances and some of the things that we want to look into is actually these third peak elements, which, if I remember correctly, it tells us something about the entropy in the if it's a neutron-star merger. It can tell us we've looked into a little bit into the actinides compared to, I think, dysprosium, which basically tells you something about the mass ratio of the two neutron stars. You can do different investigations for this, but you need a larger sample. That's
Any questions on this side? Yes. Get started.
So, all these study process are based on the study of stellar atoms, right?
Yes.
I was wondering if there are other ways trying to study this, like trying to study the interstellar movements. I guess it's really hard. Right?
Yeah. So I mean, yes, this is something that I've been wanting to do for a while, but I'm not really a radio astronomer. So in principle, the interstellar medium should have any properties that would never capture the two atmospheres stuff, right? And it would be awesome if we could find them, but this would need to be some kind of radio astronomy where you look for hydrides of some of these elements, and I have talked to radio astronomers and they can like, yeah. I think it's something that I would like to investigate. Another thing that I've talked to people about is to look for it in the spectral quasars, because there you might also see them, but the light would be extremely weak, unfortunately. Hopefully, we will. I mean, we'll probably not get another 2017 anytime soon, but they are discovering transients that they now think are actually neutron mergers due to the light curve. They're developing that. And so if we can just get more of those, then at least we can get some handle of the numbers, how often, whatever, that kind of thing. That would also be great. I think it doesn't take a whole lot of detailed information to get the right satisfaction from them, for instance. So that's one thing I'm hoping that will be more of in the future.
Just start off somebody. Oh, yeah,
Okay, so in these metallic mesh lines that you have, how will you normalize the continuum? And how the normalization can affect the resistance?
Yeah. I mean, there is continuum, right? There is a bit of continuum. And so far, most of the stars that we have looked at do have chunks of continuum that we can normalize after. But yes, it is an issue. It's a huge issue if we don't have it continuum. It helps us when we go to the room L4, and then we also try to avoid carbon impact stars because that will completely mess things up. We haven't had to dive into how to normalize these stars other than using the small bits of continuum that are actually available yet. But I have some which are called CERS stars, so carbon enhanced R process enhanced S process enhanced stars that basically don't have any continuum. So I need to figure out how to normalize those. Because yeah.
Okay. And also these stars are very, very old. And they can also be affected by fast binary interactions.
Yes, most of them are single. We have multiple radial velocity measurements for a lot of them, and most of them are single.
But if, for example, they were binaries in the past, that could mess the abundances.
Yes, in principle, yes.
You could detect that outliers somehow?
Well, yes, because I mean, presumably, if you had mass transfer in a binary system, it would be an S process because you have a more massive companion that goes through the AGP phase. Then you have an S process, then you get your material onto the star you look at. Sure, when they're then put into the lift where you could disrupt that binary system, but it would be a different abundance pattern than the R process. So it's very hard to have binary mass transfer with an R process. So yes, you could put different those.
Thanks. And a question from me about the kilonovae. How do you measure the abundances? Is that from the optical counterparts of the 2017 event? You take a spectrum.
Yeah, so they
measure.
I don't know if I had. Well, so there was a paper in Nature paper a couple of years ago where they found a feature which they believe is strontium, and then they got. Well, there's a lot of issues with that abundance because what they did was basically they just threw it through a stellar radiation transfer code and got an abundance out of that, which is highly questionable. But anyways, they threw
one line.
So basically one line, and then later the same group has identified lines they believe to be yttrium. But yeah, it's in the
James Webb or something. What was it? Or was it?
I don't think it's James Webb. I think it's actually in the X-shooter spectra that was taken from the event. Yeah, and then there was there was a James Webb spectrum also where they think they set that down to tellurium, but I'm not entirely sure about that. And whether that was the same event, I'm not entirely sure. But it's really challenging, right? Because everything is mushed together and the velocities are massive, so everything is broadened out, and you don't have, I mean, just to figure out where the lines are, where the lines should be in this fast moving ejecta, it's really hard. And I've talked to some of the people that did the strontium thing, and they're like, yeah, maybe it could also be helium or xenon. But there's a lot of work these days because of the 2017 event. There's a huge amount of work going into trying to model the spectra of these events, right? Because just figuring out the opacities and decay rates and all these things for these elements. There's a massive modeling effort going on to figure this out.
So you measure directly.
So we can actually say, okay, this is that thing. Yes. But we will never get a full abundance pattern like we get for stars. Like we will never get a neutron merger where we say, oh, well, this produced so much gold, this produced so much uranium, this produced so much silver, so much blah, blah, blah. Well, at least not in my lifetime, I don't really believe in that. Because that would be so much dependent. So yeah.
Okay. Any other questions quickly? Maybe time for one more. If there's anything, nothing online. Okay, let's thank our speaker again. Thank you very much. We can disconnect the Zoom. Yes, so we start broadcasting. Leave and I guess.